Have you ever wondered what's happening inside the mind of an AI when you ask it a question? What if I told you that even the researchers who built the powerful AI systems don't fully understand how they work? It's like having doctors prescribe medications without knowing how they affect your body. In this video, I'm going to take you inside the fascinating new research that's creating microscopes for AI systems. It's allowing us to peer inside these black boxes and discover surprising mechanisms that might just change everything we thought we knew about artificial intelligence. I'm Evan Goldstein. I'm a licensed professional engineer and a data scientist. I'm building AI capitalists to talk to the leaders and the thinkers, like you, about navigating this brave new world of thinking machines. When you ask ChatGPT or Claude to write you a poem or to explain quantum physics, there's an incredible amount of computation happening behind the scenes. But despite creating these powerful AI systems that can write essays and debug code and even create art, researchers often don't fully understand how they work internally. This is like building a brain without knowing how it thinks. Shocking reality of modern artificial intelligence. This opacity becomes even more concerning as we increasingly deploy AI systems in critical applications like healthcare and finance and legal settings. Would you trust a doctor who couldn't explain their diagnosis, or a judge who just couldn't articulate their reasoning? Yet we're rushing to integrate AI into these fields without fully understanding their inner workings or mechanisms. That's exactly what researchers at Anthropic are tackling with their groundbreaking new paper, Biology, revealing computational graphs in language models. They're developing methods to peer inside these black boxes and to understand what's actually happening when the AI generates text. It's like they're creating microscopes for AI, which is allowing us to see the invisible machinery that powers these systems. So what exactly happens inside a large language model when it answers a question? When an AI like Claude contemplates the sentence, "The capital of Texas is," with Austin, what internal steps did it take to arrive at the right answer? Did it just memorize the fact, or did it reason through intermediate steps? First identifying Texas as a state, and then recalling that Austin is its capital. These questions arise because modern language models are incredibly complex. They contain billions of parameters, and they're arranged in intricate networks. The researchers draw a fascinating parallel to biology. Understanding language models is similar to the challenges that biologists face when they're studying living organisms. Just as living creatures have evolved complex mechanisms over billions of years, language models develop sophisticated computational strategies during training that aren't directly programmed by humans. Before the invention of the microscope, the inner workings of living organisms was pretty mysterious. Similarly, until now, we could observe what language models output, but not how they arrive at those outputs. The researchers realized they needed new tools, their own version of the microscope, to examine these AI systems and identify the building blocks of model computation. So to peek inside the black box, the researchers at Anthropic developed a methodology that they call attribution graphs. Think of a language model like Claude as an incredibly complex machine with millions of interconnected parts, like artificial neurons. It's too complicated to understand directly, so researchers first create a simpler and more interpretable version that they call a replacement model. As you can see in Figure 1, the researchers replace the original model's neurons with more interpretable features that often represent human understandable concepts. This is similar to how biologists might create a simplified model of a cell to study specific processes. The simplified model doesn't capture everything, but it's designed to be easier to understand while still preserving key behaviors. The researchers use what they call a cross-layer transcoder to build this replacement model, which translates the complex activations of the original model into more interpretable patterns. They also add error nodes to represent the parts of computation they can't interpret cleanly. Now, once they have this more interpretable replacement model, the researchers compute attribution graphs that show how information flows through the model for a specific prompt. Think of an attribution graph as a map showing the journey of ideas through the model's mind, and it shows which features activate, how they influence the other features, and ultimately, how they lead to the model's output. For example, in one of their key experiments, they analyzed how Claude completes the prompt, "Fact, the capital of the state of containing Dallas is ... The attribution graph reveals fascinating insights. So let's look at Figure 5 and 6. Here we can see how the model first activates. So here in figure 5, we can see how the model first activates features representing Dallas, which then activates features representing Texas, which in turn activate features representing Austin as its capital. This visualization is showing us a genuine multi-step reasoning that's happening inside of the AI. The researchers could verify this through intervention experiments. So here we see a variety of different paths that the AI used to get to the answer Austin. So these researchers could verify this through intervention experiments that are shown here in figure 7. In these experiments, they modify the activations of specific features and they observe how this affects other features and model's outputs. For example, they inhibited the Dallas features, and that decreases the activation of Texas features, and it changes the model's output to other state capitals. So you see on the bottom corner here, when that is depressed, when the word Dallas is depressed, now it's spitting out Albany, Springfield, and Sacramento. Those are capitals of other states because Dallas has been suppressed. This is confirming that the computational paths identified in the attribution graphs genuinely reflect causal mechanisms inside the model. Figure 9 shows even more powerful evidence. When they swap Texas features for California features within the model's internal representation, the model outbursts Sacramento instead of Austin. When they swap in Georgia features, it outputs Atlanta. These intervention experiments are demonstrating that the model is genuinely using these internal representations to determine its answer. In another fascinating case study, they examined how Claude writes rhyming poetry. You might think that the model would just improvise line by line, but look at figure 10. And what the researchers are finding is that the model often plans ahead, and it activates features corresponding to potential rhyming words before even beginning to write a line. They found evidence that the model would identify a target rhyming word like rabbit, and then work backward to construct a line that would naturally end with that word. So if we're looking at figure 25, it shows the operand plots for different addition features. Now this is a case where the model was asked to perform a simple addition problem. The model uses multiple parallel pathways, and it combines rough estimation with precise calculation of the ones digit. This is showing that AI systems are developing their own unique cognitive strategies that are different from human approaches. Think about the standard stacking algorithm, as they call it, where let's say you did 11 plus 12, you would do 1, 1 plus 1, 2, and then you would add the ones, get 3, add the tens column, get 2, and you get 23, right? In this case, what it's actually doing is sort of homing in on the value by estimating in different ways. But here's the key. When it answers, when Claude was prompted as to how it got the answer, it went through the regular algorithm and it explained it to the user as if it had used the standard stacking algorithm. So it's not really telling you what it's actually doing. It's telling you what it thinks you want to hear in a way. The ability to peer inside AI systems and to understand how they work has profound implications for all of us. Think about it like a car. Most of us use cars daily without understanding exactly how the engine works, and that's fine for normal driving. But what if your car started making unusual decisions, like sometimes turning left when you steer right? Suddenly, understanding the mechanism becomes crucial for safety and reliability. And if you're getting value from this content, I would appreciate it if you'd push the like button. Pressing like lets me know that I'm making content you want to see, and it spreads that content to others. Let's break AI capitalist out of small channel hell together. Similar to this, AI systems become more integrated into our daily lives, and now they're making decisions in healthcare and finance and education and more. So understanding their internal mechanisms is much more important. The methods developed in this paper could help medical professionals verify that an AI is using medically valid reasoning rather than spurious correlations. For example, in a medical case study from the paper, which is figure 30, it shows how Claude reasons through a diagnosis by activating features related to symptoms, possible conditions, and appropriate follow-up questions. In the case of a pregnant woman with concerning symptoms, they found that the model internally represented concepts related to preeclampsia, which is a dangerous pregnancy complication, even though the term wasn't mentioned in the prompt. So for example, in a medical case study from the paper, figure 30 shows how Claude reasons through a diagnosis by activating features related to symptoms and possible conditions and appropriate follow-up questions. In the case of a pregnant woman with concerning symptoms, they found that the model internally represented concepts related to preeclampsia, which is a dangerous pregnancy condition, even though the term wasn't mentioned within the prompt itself. And then here's a mapping of sort of how the concepts moved through the model. And here in figure 31, it's showing what happens when they inhibit the model's internal representation of preeclampsia. The model is switching to suggesting symptoms related to other diagnoses. This is suggesting that the model is genuinely reasoning about potential diagnoses internally. These methods could also help identify when models are using flawed reasoning. For example, when researchers examined how Claude handles questions about unknown people, like which sport does Michael Batkin play, they discovered a fascinating mechanism, which is shown here in figure 33. The model activates can't answer features by default when faced with a name, and only suppresses these features when it recognizes the name of someone that it knows information about. This helps explain why models sometimes correctly admit ignorance, but at other times they hallucinate false information. By understanding how current AI systems work internally, the researchers can design better systems in the future. Just as understanding biological systems has led to better medical treatments, understanding AI systems could lead to more capable and reliable and beneficial AI. So the paper from Anthropic presents a very big advancement in AI interpretability, but it's important to consider its limitations and how the broader research community is responding to this. The researchers themselves are candid about the limitations of their approach. They say that their attribution graphs provide satisfying insight for only about a quarter of the prompts that they tried. It means that 75% of cases showed methodology that either doesn't work well or it provides incomplete explanations. And they stated in the paper, like any microscope, our tools are limited in what they can see. This is a crucial acknowledgement. While the method provides valuable insights, it's far from a complete solution to AI interpretability. One major limitation is that their method doesn't capture how attention mechanisms work in transformer models. Attention is a big component that determines how information flows between different parts of the input. But the attribution graphs treat attention as a black box. This is a significant blind spot because a lot of complex behaviors and language models are big on attention. Another limitation is about the quality of the features that are identified by the cross-layer transcoder. The paper acknowledges that features are often difficult to interpret cleanly and may represent multiple concepts simultaneously. So the feature splitting problem means that what appears to be a single concept, like Austin, might be split across multiple features, and it makes it hard to trace how the information flows through the model. So I gotta say, at least they were being honest about the limitations. It's gonna be hard to put this into practice with current AI systems right now because everything has to be done manually. But this is a big first step to actually getting into the black box and seeing what's going on inside. So we're standing here on the frontier of artificial intelligence, and we have increasingly powerful systems that are becoming integrated into the fabric of society. So the work that these scientists have done presents more than just a technical achievement. It's speaking to a deeper question about our relationship with the intelligent systems that we're creating. The biological metaphor that's at the heart of this research really gets to that idea, because just as biologists spent centuries developing tools and methodologies to understand living organisms, we find ourselves at the beginning of a similar journey with artificial intelligence. So just like the microscope revolutionized biology, attribution graphs and the related techniques might be the first generation of tools that let us peer into the minds of our AI systems. Figure 32 shows a particularly striking example of how these tools can work in action. We see how the model decides whether it can answer questions about particular entities. The model actually has a known answer and known entity features that inhibits its tendency to refuse to answer questions. So this raises a lot of philosophical questions. If artificial neural networks, which are trained through relatively simple algorithms, develop complex mechanisms that even their creators can't understand, what does this tell us about our own intelligence? Maybe the complexity that we see in biological systems and human cognition is emerging from simple underlying principles. Now, the fact that we can now start to look inside these black boxes has a lot of effect on our ability to trust and hold these AIs accountable. As AI systems are taking on more important roles in society, the ability to verify their reasoning processes is critical. We wouldn't trust a doctor who couldn't explain their diagnosis or a judge who couldn't articulate their reasoning. We should be cautious about delegating important decisions to systems whose reasoning we can't understand. But we're on the early days in this journey, and our tools for understanding AI are imperfect and incomplete. The most profound insight from this research is the recognition that intelligence, whether it's biological or artificial, isn't easily reduced to simple explanations.